We start with a 40-minute presentation, followed by a Q&A from the audience, and ending with a feedback and discussion section with Karl. And I see we are recording, so that's perfect. And today I'm delighted to introduce Robert Pepperell. Robert is a professor at Cardiff Metropolitan University, and his work aims to better understand mind and nature by integrating art, philosophy, and science. So without further ado, I'll pass it on to you, Robert. Thank you very much for joining us today.
Great, thank you, Christoph. I'll hopefully you can see my screen okay. Yeah, so thanks for the invitation. Looking at the list of other talks you've had recently, I think this probably is a bit of an outlier, I'm guessing. I don't know, in terms of the content I'm going to cover, but I do hope it links to what you're interested in and what many of you are researching. Even though I come from a different sort of disciplinary tradition, yeah, primarily from an art and I guess philosophy background. But I'm going to talk about the biophysics of beauty, unifying art and science, and to explain what I mean by that. Sorry, is this in the way here? Was that okay? To explain what I mean by that, we tend to divide nature into discrete layers for the purposes of study. I mean, there's many ways it could be done, but this is sort of common demarcation with physics at the bottom at a sort of foundational level, and maybe aesthetics or high-level cognitive processing at the top, and then chemistry, biology, and neurobiology, and so on in between. But we also know that nature doesn't work like that. It doesn't divide itself into discrete layers, and those layers don't operate independently of one another at all. So if we think about something like a person experiencing a work of art and having a kind of strong aesthetic experience, we know that involves activity at all these levels. There's physics going on there, there's chemistry going on, there's biology going on, and so on. So nature is integrated in that sense, in a way that perhaps our kind of scientific approach to analyzing it doesn't necessarily accommodate. So to try and explain what's going on at all these layers, ideally we'd want to do that with as few principles as possible. Ideally we'd want something that explains what's going on in nature from a ground level physical state up to high level cognitive states like aesthetic experiences, with neurobiology sitting somewhere in the middle of that. And this is really what I mean by unifying science and art, finding some common ground, some common explanatory principles that allow us to satisfactorily explain what's going on across all these levels. As few as of those principles as possible. Perhaps even there is one overall overarching unified principle we can find that helps us to do that job of explaining nature at all these levels. And perhaps the closest we've got to that at the moment is what could be called the free energy principle, which is obviously strongly associated with the work of Karl Friston. I hope Karl doesn't mind me having made this drawing of him. And arguably it provides the most unified framework we currently have within which to study phenomena at many levels. It's certainly been applied to the study of nature at many different levels, through the active inference framework or the predictive processing framework, which I'm sure all of you are very familiar with. And so when Karl talks about the physics of sentience, this is really the same thing as I'm talking about here when I talk about the biophysics of beauty. That is, how do we connect, very, very low level fundamental activity in nature with very, very high level cognitive, aesthetic, sensory and sentient processing. But despite the success of this framework, which has been great. So I should just mention, actually, I did a paper a year or so ago for a special issue of Philosophical Transactions that Karl also contributed to, looking at the relationship between art, aesthetics, and the predictive processing framework. And even though I'm by no means, I'm very far from being an expert in that way of thinking about the world, I did, through writing this paper and talking to various people during the process, come to appreciate at an intuitive level at least, the power and scope of the approach, the kind of explanatory power of it, particularly when you start to apply it to think about how we perceive works of art, and in fact how we make works of art. I talked a lot about my own art process and how predictive processing approach helps to cast light on some of the processes that are going on in there. But despite the power and scope of that approach, clearly many deep challenges remain, and these are some of the ones that particularly interest me. There are obviously many more. For example, the neurobiology of pain and pleasure, it still remains largely mysterious, I would say, as does the neural basis of affect and aesthetics. I've done a lot of work in empirical aesthetics and experimental aesthetics, and whilst we've made great progress, some really fundamental questions remain. The notorious hard problem for consciousness, which we don't seem to be much closer to solving despite the efforts of many people around the world. And I think the related question of the origins and nature of life, all these remain outstanding questions that we still need to find some way of making progress on at a deep level. So the outline of the talk today is to sort of address some of those challenges by talking about a set of principles of nature that were very prominent in the 19th century and early 20th century, but seem to have sort of moved into the distance somewhat. They're not very widely discussed anymore, to the best of my knowledge. And there's 5 of them. I'm going to introduce them all very briefly and just give you a sort of a mini overview of each of them. You may be familiar with some of them or some versions of some of them, and I'm not going to deal with them comprehensively, but I'm just going to introduce those principles. And what I want to try and demonstrate today is that they all have explanatory potential and can actually generate testable predictions, despite the fact that we don't really, that they're not often sort of treated as prominent theoretical positions today. But using new tools and methods, we now are able to look at them in a new light. And really the main point I want to make is that these 5 sets of principles have a commonality, which points to an even more general principle, which also may complement the active inference framework I mentioned at the beginning. So to start discussing those principles, I'm going to start with something actually that comes from Michael Faraday. And I'm sure you all know the importance of Michael Faraday as a physicist and a chemist. I think he would have talked about himself as a natural philosopher in the 19th century. And in 1854, when he was at the sort of height of his prestige and influence as a scientist, he was sent a book, this book actually, by an author called Woolnow, which was the first manual on paper marbling published in the English language. Paper marbling was a very secretive art that was practiced by people, which was largely the methods and skills and tools that needed to do it were kept very, very secret as a kind of trade secret. And Woolnow published this first kind of textbook on how to do paper marbling. And if you don't know what paper marbling is, it basically involves dripping paint and ink onto the surface of a specially prepared bath of water. And because of the way the bath is set up, rather than sinking to the bottom, the ink rests on the surface and forms these kind of beautiful patterns, these cell-like shapes and patterns quite spontaneously. And normally once the pattern's created, the marbler then lays a piece of paper on top and takes a print and dries it. And that's the marbled paper that's used in bookbinding. Michael Faraday was trained as a bookbinder as a young man. He was apprenticed to a bookbinder. As he knew intimately about the process of marbling and its use in bookbinding. And when he received this book, he wrote back to the author with this little note saying, "I beg to thank you for your kindness in sending me a copy of your very practical work on marbling. I feel much interest in the subject because of its associations with my early occupation of bookbinding, and also because of the very beautiful principles of natural philosophy which it involves." And when I saw this phrase, it really jumped out at me. the beautiful principles of natural philosophy, because I immediately wondered what he meant by these beautiful principles. You know, we tend not to think of science and beauty in the same conceptual framework, but I think Faraday did. You know, Faraday very frequently in his notebooks talks about the beauty of the processes that he was observing in the lab, and it's probably things like this he had in mind. You know, here's some examples of some drawings made from what he called the lines of force that surrounded magnetic objects, which Faraday made by dropping iron filings on top of paper over magnets, revealing these lines of force. And I used a similar process actually to make this piece of art a couple of years ago, using ferrofluid, which is a kind of magnetized fluid suspended in resin with ink, showing the same principle, the lines of force around a magnetic field, around a magnetic object, which has this kind of cell-like, naturalistic, organic pattern to it. So I think this is what Faraday is referring to by these natural principles, these beautiful principles. And in a lecture he gave, one of his Christmas lectures actually, towards the end of his life, he talked about the beautiful laws by which we grow and exist and enjoy ourselves, and I'll come back to enjoyment in a minute, all of which are affected in consequence of the existence of certain forces or abilities to do things or powers that are so common that nothing can be more so. And so this is kind of, at the end of his life, Faraday summing up his view of nature, which was very unified. He had a very unified understanding of the different forces at work in nature, and said that nature consists, in the same lecture, nature consists in the universal correlation of the physical forces of matter. So he had this very kind of profound understanding of the deep correlation between activity and visible phenomena in nature and their underlying causes. The second principle I want to mention is the energy minimization principle. It goes by different names, and it's distinct from the free energy minimization principle, I'll come back to. But it's this general idea, which you'll all be familiar with, that a system that has energy tries to find some kind of equilibrium where the energy is as widely distributed as possible. And so this ink drop dispersing itself in water is an example. And often reminded, actually, a talk Karl gave some time ago, where he talked about the drop of ink going into the water and dispersing in relation to the free energy principle. And this is one of the things that sort of triggered my thinking that there's a deep correlation between these different kinds of energy minimization, which I'll come back to later. But one way to state the energy minimization principle is to say that the system tends to minimize its free energy. And by that, I mean energy is defined here as the capacity to do work. So that's the sort of traditional 19th century thermodynamic definition of energy. And free energy is the energy available to do work in the system in order to reach a state of equilibrium where all the forces in the system are balanced. So it's a quite traditional thermodynamic definition of free energy minimization. But actually, marbling is quite a nice illustration of that process in action. So here's some marble pieces that I've made. And what you can think of them as a kind of map, really, of the free energy minimization that's going on throughout the marbling process. So when you add ink and paint to the marbling system, you're really adding energy, whether it's chemical or kinetic energy, into the system. And all the forces that are unleashed by that energy have to find some kind of stability, some kind of equilibrium or balance in the system as a whole. And once all those forces have settled down and the pattern has kind of reached its fixed final state, that's the marbled image that you take. So these images are, in a sense, a kind of, as I say, a kind of map of the equilibrium state of the system once it's reached stability. And I quite often think of these marbling pieces when I'm making them in relation to Karl's idea of the Markov blanket, because these Markov blanket, or these little sort of cell-like forms, which, as you saw, kind of form quite spontaneously when you drop the ink and paint on, are partly formed by the forces within the. So if you look at one of those sort of brown cells, for example, in the image on the left, they're formed by the internal forces acting within that kind of shape, but also by the external forces acting upon them. And it's the equilibrium or balance between those forces that ends up producing the final pattern. And I'll come back to this later, but it does strike me as having some similarities in terms of a physical process with what's known in other contexts as the Markov blanket. And if this is of interest, there's a paper that came out last year on this, looking at the sort of physics and chemistry of marbling process, which you can see down on the left here, how that plays out in traditional paper marbling of the kind that Faraday would have been familiar with, that's used in bookbinding and so on, and also how those same principles seem to apply in natural forms. We see particularly cells, things like Bernard convection systems and so on, which seem to be operating, at least in some ways, along similar principles. The third principle I want to introduce is the pleasure principle. Again, some of you will have come across this, I know. It was largely introduced by Gustav Fechner, and Gustav Fechner was active in Germany throughout most of the 19th century. He's not as well known as I think he should be, given his influence on subsequent generations of scientists and actually philosophers too. He was trained and practiced as a physicist as a young man. He's probably best known today as a founder of experimental psychology, and the method of psychophysics that he developed is now very widely used still by psychologists. But it's probably how he's best known today. But he was also founded the field of empirical aesthetics, which is an area I've worked in. And one of the interesting things about Fechner is that even though he worked in all these different areas, for him, they weren't separate areas of study. He was looking for these kind of deep underlying unifying principles of nature, which found expression in physical processes, in psychological, and in aesthetic processes too. And the pleasure principle was one of his most important fundamental ways of thinking about nature. One way to state it is that avoidance of pain and striving for pleasure are fundamental drivers of behavior in physical systems. Systems incur pain when moving away from stability, as Fechner called it. We could read there perhaps equilibrium or homeostasis, and they gain pleasure when moving towards stability. And importantly, it's the change in free energy in a system that induces that stability or instability. So increases in free energy drive a system away from stability, while decreases promote stability, according to Fechner. So just a couple of quotes to illustrate his thinking on that. No motive exists that is not directed to creating or maintaining pleasure, or eliminating or preventing displeasure. And in a quote that actually seems to have some resonance with ideas in active inference, for example, linking action to feeling, he said, "No measure can be more linked to action than what lies immediately in feelings. The principle of pleasure is a computational principle." And it's interesting that he's talking about it in computational terms in the mid-19th century. And I'll come back to that idea of computational expression of the pleasure principle shortly. Many people supported and endorsed the pleasure principle throughout the 19th century and into the 20th. I've just given a brief sample here of some prominent scientists from different backgrounds, including Ernst Haeckel, one of whose images there is on the right, showing more cell-like forms. But probably the person most famously associated with the pleasure principle is Sigmund Freud, who took it from Fechner. He credited Fechner with originating the principle and said more or less, that Fechner's expression was the one he was developing from. As Freud put it, the function of the pleasure principle is to make the psychical apparatus lack energetic excitation, or to keep excitation constant, or to minimize it as much as possible. So a different way of expressing the same thing in a different scientific context. So just to show that sort of generalized from that work and express the free energy principle in this sort of diagrammatic sense, we can say that the tendency to minimize free energy as the system seeks equilibrium is psychologically valenced. That is, increasing free energy, moving away from equilibrium, has a negative valence, and decreasing it towards equilibrium has a positive valence. And that's really what's illustrated in that little diagram below. The fourth principle is the psychophysical principle. Again, some of you may know about this. I've come across it in different contexts. Again, it's attributable largely to Fechner, who developed this in the 19th century. And according to Fechner, we can treat all natural systems as having two parallel aspects, a physical and a psychological. And the common currency between them, again, is energy. So this is one way Fechner tried to explain the basis of the psychophysical principle. Any system has two aspects. One physical aspect we can observe from an external point of view. So by analogy with the full moon, this is the side of the moon that reflects the sun back, the side we can see. But every system also has an unobservable psychological aspect to it. By analogy here, the dark side of the moon. And for Fechner, these were not two separate, distinct kinds of domain or substance. He saw them as intrinsically integrated into one single object. So there's only one moon, but there are two different ways of considering the moon, one external and one internal. And one way Fechner put this in his textbook on psychophysics in 1860, what will appear to you as your mind from the internal standpoint, where you yourself are this mind, will, on the other hand, appear from the outside point of view as the material basis of this mind. And that was his kind of fundamental starting point, really, for all the physics, psychophysics, psychology, and aesthetic experimental work he did. This psychophysical understanding of nature, not just actually in living systems or sentient systems, but for Fechner, this was applied to systems of all kinds, inanimate, inorganic, as well as living. As I mentioned, the common currency is energy, either physical or, as he sometimes called it, psychical energy. And in the same textbook, Fechner says, kinetic energy employed to chop wood and kinetic energy used in thinking, that is, the underlying psychophysical processes, are not only quantitatively comparable, and I'll come back to that, but each can be transformed into the other. There's two aspects to energy, one physical, one psychological, according to Fechner. And of course, when you link that back to the pleasure principle, mentioned a little earlier, changes in energy, positive or negative changes in energy, which can be observed externally, have an internal, unobservable change in valence associated with them because of the intrinsic connection between those two kinds of properties. And then the final principle is the aesthetic principle, and this is largely developed by the founders of the Gestalt psychology school in the early 20th century, primarily Kohler and Kofka, and it drew very heavily on Fechner's psychophysical energetics, but also Faraday's and Maxwell's field theories. So what the founders of Gestalt psychology were looking for was a physically grounded model of mind and effect. They were trying to explain not just aesthetic properties, but also cognitive and mental properties more widely in terms of fundamental physical principles based on force, tension, and energy minimization. So just to illustrate that with a brief quote from Kohler, who I think I'm right in saying studied actually physics with Max Planck when he was a student, and so knew about contemporary physics, said that all processes which terminate in time independent, I think he meant by that static or stable states, in all these processes, sorry, the distribution shifts towards a minimum of energy. And that for Köhler was a sort of, that's another way of stating the energy minimization principle I mentioned earlier. And they developed this idea in terms of the connection to the mind. So Kafka, for example, said, if nervous processes are physical processes, then they must also fulfill this condition, this minimization of energy condition. In terms of aesthetic theory, this was probably most highly developed by Hans Eysenck in the 40s. And this quote appears frequently in the empirical aesthetics literature. It's this kind of culmination or summation of much of the research that preceded on these principles. And Eysenck defined the aesthetic principle in the following way: the pleasure derived from a percept as such is directly proportional to the decrease of energy capable of doing work in the total nervous system as compared with the original state of the whole system. He could have said, but didn't, that the opposite is also the case, that the displeasure derived from a percept would be proportional to the increase of energy capable of doing work. So very briefly touching on those principles, I hope you can see already that there's a lot of commonality there. They each have slightly different backgrounds and histories, but there's a lot binding them together. And I would argue, in fact, they're all deeply related to one another. And what I just want to do for the remainder of this talk is to sort of treat them as almost as a single principle, just sort of bundle them together. And for convenience sake, I'm going to call them the psychophysical free energy principle. It's not a very elegant label, but hopefully shortly you'll see why I've labeled it in that way. And so the psychophysical free energy principle combines several established principles, as I've just mentioned. It treats the world, for scientific purposes at least, as a psychophysical object of study, where each object has a material and a mental side. And it's related in all kinds of interesting ways, some of which I'll touch on very shortly, to the active inference free energy principle. So really, I'm just sort of comparing and contrasting these two ways of talking about the free energy principle in this context. Now, it's not just a theoretical position. In fact, for most of its history, this psychophysical approach was largely theoretical. There wasn't really a way to test it under laboratory conditions, for example. But I want to argue that in recent years, particularly in the last 20 to 30 years, a whole range of new tools and methods have become available that now allow us the opportunity to test this psychophysical framework in a way that wasn't possible to many of the people who originated it in the 19th and early 20th century. For example, we can now produce very high resolution images of neurobiological processes and correlate them reliably with psychological states. But in order to carry out these tests, in order to find out whether there is experimental value in this psychophysical approach, we need to define it in a much more rigorous way and a much more quantitative way than it has been done traditionally, in order to subject it to the experimental paradigms we might want to investigate. And this is essentially what I've tried to do in this book, which came out recently. So the purpose of this book is really to take this psychophysical framework, to define a new set of psychophysical properties that can be experimentally measured and mathematically modeled, to set out the experimental tools and methods by which we might investigate their value, and make some testable predictions, and then consider what the explanatory potential would be if those predictions were confirmed experimentally. And really the heart of the book, or the main proposition of the book, is summed up in this table here. And I'm not going to go into it in great detail now. We can come back to it later if you like. But it's essentially what it does, and it's very, very speculative and conjectural. So it's entirely subjective. It's entirely dependent on future testing, but it's a starting point. What it does is it takes the many of the standard physical properties or quantities that we use every day in science, things like energy, mass, acceleration, and so on, and makes a principled guess at what the equivalent psychological quantity might be. And there's a kind of rationale behind each of the proposed psychological quantities, but there's every chance that, as proposed here, they may be entirely wrong. But at least it is some kind of starting point for quantifying this psychophysical framework that Fechner originally proposed. So one of the key ones, so sorry, you see in the green column there is the standard physical quantities, and then the pink column are the proposed psychological quantities that parallel with them. The key one is the parallel between experience and energy, and this goes back to what I was saying before about Fechner. He made essentially that same connection. But the two I want to draw attention here to today are the one in pink here, distress, and the one in blue, relief, which are the equivalents of the valence I spoke about earlier, the positive and negative valence that depend on the direction of energy change in the system. So just formalize those quantities, and we can start to think about how these might play out in a physical system. So let's just take, for example, a very simple thing like a spring system. When that is pulled away from its equilibrium state, when energy is added to it, then it's pushed away from its state of repose, as I called it, and it undergoes distress, which is the pink area there in the graph on the right. As it relaxes back to its equilibrium state, it undergoes relief, which is the blue area. And you can see the parallel energy and experience quantities at the very bottom of the spring there, moving in synchrony as the system changes. So just to sort of push that point home, just so you get the idea, this distress part of the graph is the negative valence, and the relief part is the positive valence, depending on the way the energy is flowing. I had an attempt at modeling this in a simulated gas system. I've got some help with a physicist to do this, and it's a very, very simple system. It's very much a first attempt to try and kind of model these psychophysical properties in some kind of physical context. It's a box of particles. You can see in the top left from the code there. In this case, it's 200 particles. You can modify some of the conditions, like the temperatures of the walls and so on, as you could in a similar in a normal physical simulation, particle simulation. But where it differs is in this respect, in the pieces of code on the right there, where you see that the quantities of relief and distress have been also coded into the model based on the direction of change of energy. And this is an animation from a trial run of the system. And you can see there that where the particles are gray, there's no energy being transferred. So they're at equilibrium or in repose. But where they either flash blue or red is an indicator that they are, at that moment, experiencing either distress or relief, depending on the direction of energy flow from one particle to the next. So this is, in a sense, observing the behavior of a physical system in the way we normally would with a particle simulator, but we're seeing something we wouldn't normally see, arguably, which is the psychological state of the particle or the particles as the system evolves. And just to show you what's being tracked here, on the left is a graph showing the change in the velocity, the average velocity in the system over time, and then on the right is the average distress and relief of the system over the same time period. So what that's doing is just taking the average distress and relief at each point during the trial run, and arguably what this is presenting us with is a new kind of macroscopic property of the system based on the behavior, the microscopic behavior of its particles. So it's giving us a sort of readout, if you like, of the psychological level of distress or relief that the system is undergoing as the particles interact with each other. So this is a very, very kind of simple first draft proof of concept, if you like, just to see whether it's possible in principle to integrate these psychological properties, these psychophysical properties, and track them over time. In theory, though, we could do the same thing with a real neurobiological system. So, for example, if we think about the fruit fly brain, the Drosophila brain, we know that fruit flies feel pain. It's widely believed that fruit flies are able to feel pain, perhaps sexual arousal. And this paper was published a few days ago, showing that they can play. They enjoy riding on this carousel. Hopefully you can see that in the through the screen share. And they seem to do this for no kind of nutritional or reproductive benefit. It's just something they seem to do because they enjoy it. So potentially at least these creatures are capable of feeling something like pleasure. The other thing, you'll know this much better than me, but we have very good understanding of the nervous system of the fruit fly, and we can do very kind of high-level, high-resolution neuroscience. So here's an experimental prediction, and we could take maybe the fruit fly neurological system as an example here to test this. If the positive energy gradients in the relevant regions of a nervous system predominate on average, then the creature would be experiencing pain, as indicated on that graph on the right. Conversely, if negative energy gradients in the relevant regions of the system predominate on average, then the creature would be experiencing pleasure. And that's really just another way of restating the pleasure principle mentioned earlier on, but looking for specific neural markers of that in a real nervous system. Now, I simply don't know enough about neuroscience to even know where to begin to look for these markers. But speaking to neuroscientists about it, there are plenty of ways in which we can observe energy changes in neural systems, which might give us clues as to the link between the direction of those changes and the if you like, the valence state or the experience of the system, and how it correlates with those changes. So to try and draw all this together, the psychophysical free energy principle I've mentioned here, it comes largely from the work of Fechner. It comes from a sort of thermodynamical view of the world. It's largely dealing with biophysical work, that is, the transfer of energy amongst matter to do work. It links to the psychodynamical ideas of Freud and Gestalt theory, Gestalt psychology, as I mentioned. And the key idea here is that valence is an intrinsic parallel of what is observed extrinsically as free energy gradient changes. And I'm sure you will have spotted already a number of ways in which this seems to parallel or relate very closely to the active inference free energy principle, as I've called it here, which is associated with Karl and his colleagues' work he's done, which comes from a slightly different tradition in the sense of relying more on statistical mechanics, on machine learning, on Bayesian probability and information theoretical tools. But there are a number of points where they seem to be either overlapping or potentially converging, and I'll just mention a couple very briefly. A paper by Gioffoli and Corricelli from, I think, 2013 made a similar sort of connection between valence and the rate of change in free energy over time. And Mark Solmes's work, some of which has also been done with Karl, linking free energy minimization to pleasure and pain, with his emphasis on feeling and affect. So this is a slightly cheeky proposition, but it certainly has some potential value in it. If we think about the free energy principle as the apple here in the middle, Perhaps from a Fechnerian point of view, looking at it through the lens of psychophysics, it appears one way. Looking at it from an active inference framework perspective, from Karl's point of view, it has a slightly different aspect, but perhaps these are just two different ways of looking at the same thing, and there's some more inclusive way to think about the free energy principle that perhaps tracks back to what Faraday was talking about in that quote I gave you far earlier on, about these beautiful principles that seem to encapsulate nature at many levels, including our enjoyment of things in the world, our pleasures and our pains. So in closing, I just want to throw in what I think is a very interesting potential research question here. In fact, I should say that it was seeing a talk by Karl some years ago talking about this work in a paper, Life as We Know It, that I think triggered this whole line of thought, in my mind at least, that we might be able to kind of physically model these psychological properties of natural systems. And perhaps there's a potential here to model the psychological properties of systems in parallel to their physical properties, and to find out whether this would provide a more comprehensive explanation of the psychophysical behavior of the system, what's going on internally from its own psychological perspective, in parallel to what we can observe externally from its physical perspective. And so to summarize, I've mentioned some principles of nature that were widely discussed and proposed in the 19th and early 20th centuries. I've suggested that we can find deep and common ground between them, and that they do seem to have explanatory potential, and maybe even point to some more fundamental general principles than we are currently aware of. This psychophysical free energy principle is amenable to testing and modeling and can generate falsifiable predictions. It has a lot of common ground with the active inference version of the free energy principle, and in fact they may be identical, different ways of looking at the same thing. There's potential opportunity to integrate these versions into a more holistic psychophysical framework of the kind that I think Fechner had in mind throughout his career. And any results from that work may increase the explanatory range and power of our models. And with that, thank you very much. Thank you.
Thank you very much, Robert, for this delightful talk. Quick unmute and round of applause, please. Very interesting talk. Thank you so much. Also for sharing your art. I think that was a really nice touch. Do we have some questions from the audience?
I have some questions.
Yeah, please go ahead.
Yeah, I really appreciate this, Robert. I'm a psychiatrist, and so a lot of what you said is very relevant to things that I think about every day. And so just to kind of synthesize, because you started out with talking about beauty, and I just tried to write down my understanding of what it is you were saying. And here's like a short version of it. Like, beauty is a process of drawing our attention towards something combined with an intrinsic sense of reward for having merely engaged with that thing. And maybe even you could say ugly is a process of drawing our attention towards something combined with an intrinsic sense of disgust for merely having engaged with it. Does that sound like a relatively decent synthesis of what you were saying?
Yeah, no, I think that would be broadly true, and but I think the notions of reward and disgust and so on, which are very, very useful and are used all the time in psychological research, and in particular in the field of empirical aesthetics, which is the area I've been involved in mainly. We clearly know what we mean by them, and we can measure them and track them to a great extent. I think that what remains unknown, though, is how they are, how they come into being, if you like, within our neurobiological system. So, where we can plot say, neural correlates, if you like, of those experiences. How are we explaining why those correlates are as they are? So I would broadly, totally agree with your characterization of the phenomena, but the problem remains of how we then explain the difference between them and how we might kind of find that difference somehow expressed in the neurobiology of the system.
That sounds like a problem that Lisa Feldman Barrett describes when she talks about just like emotions in general and how they're kind of degenerate phenomenon in the brain where it's very hard to see that one person's joy maps even later in the same person to the same process that it would in another person. So it's a very difficult question.
Yeah.
I also was wondering about, so I think you mentioned something about pleasure, increasing energy available to do work, and maybe displeasure increasing or decreasing energy available to do work. But one of the ways that I think about that is it's that they actually both increase energy available to do work, but kind of in a valenced way, like you were talking about later. There is pleasure, there's displeasure, the opposite of pleasure, but then there's also like not even noticing something or caring at all. And so that's like the no change state. But in both pleasure and displeasure, there is a motivation toward doing something about it, I guess.
Absolutely, yeah, and I think Fechner says this in one of the quotes I gave, that this is a fundamental motivator of behavior and action. It's an interesting question. I haven't whether we get rewarded for behaving in a certain way or whether we behave in a certain way because the principle of motivation is there. Maybe something both are happening at the same time. And of course, as you hinted at, I think lots of human experiences are not simply binary pleasure or pain. You can't just, sometimes they're mixtures of two. I know this from a lot of work in aesthetics, for example. Ugliness can be a positive value as well as a negative value. It's not just about positive emotion. Lots of artworks are very unappealing and quite challenging and upsetting sometimes. So it quickly becomes incredibly complicated, particularly at a high level. But that doesn't necessarily mean that there aren't some fundamental principles underneath that sort of driving that motivation, that behavior, particularly if you're looking at simpler organisms. Perhaps we stand a better chance there of disentangling this, which is why I mentioned the fruit fly is by no means a simple organism, I know, but it may be more tractable in that context than the very, very complex and reified experiences that we have as humans. Yeah.
And then I think the last thing before I stop, you mentioned that there can be, or there's a concept of converting psychic energy into kinetic energy. So there's kind of an equivalence there. At least you can make that equivalence mathematically and even philosophically. And that kind of reminded me of something called panpsychism, which has this idea that like there's consciousness imbued in everything and that it's sort of like equivalence. There's an equivalence. Is this a related idea?
It is, yeah. I tend to avoid using the phrase panpsychism because I'm not totally convinced that the way it's currently defined is helpful. I mean, the way that most people define it is that consciousness is a ubiquitous and fundamental property of nature. And I try to distinguish between experience and conscious experience. So I'd rather say that for experimental and scientific purposes, we can assume that all systems have some kind of experience, which is basically comes from Fechner. But it takes a very special kind of system operating at a very, very specific way to produce the conscious awareness that we have particularly as human beings and lots of other animals share. So I would say conscious experience is a sort of separate category of, and quite a rare example of something that's very much, very widely distributed. So it's just making that distinction, I think, is helpful. But yeah, broadly speaking, there's a long tradition of thinking in this way about nature, of which Fechner is only one example. many philosophers, scientists have thought about a mental aspect to nature of some kind that is playing a role somehow in the behavior of the world we see. And certainly I think that's something we should take seriously. Yeah.
Thank you very much. I appreciate it.
Thank you. Thanks for your questions. Thank you.
Thank you, Ryan. Ali, your question?
Yes, thank you so much for your fascinating presentation. Well, actually, this topic interests me a lot because this is what I've been thinking about, in recent months. But I had a comment to make and then probably a question. I'm not sure if you're familiar with this preprint by Delhi et al., Delhi, Scholler, and Adam Safran, which was released a couple of months ago, called Feeling the Heat, a Thermodynamic Perspective on Emotions, Motivation, and Time Perception. Because what you've just presented looks to me very, or at least their work is very relevant to what you've been doing. So I just wanted to mention this preprint because but the main difference between your perspective and theirs, it looks to me is, but correct me if I'm wrong, but it looks to me that you're not so much concerned with the time dimension, or more rigorously, the time perception dimension of your framework, but they've just put that valence spectrum across both thermodynamic, from a thermodynamic perspective regarding the intensity and mapping that onto the valence spectrum, and also on the time spectrum, because as we know, time plays an important role in, at least pinning down the precise valence, because the intensity alone maybe would not suffice to make a very precise claim about the or at least to quantify the valence in a very precise term. But I was also wondering whether you're familiar with Deleuze's work on affect, because Deleuze's work, inspired by Spinoza's use of the term affect, his use of this word goes far beyond what we usually mean by affect or emotion, or he also uses this term to refer to inorganic life and inorganic affects and emotion, not so much emotion but affects, particularly the distinction he made between the affects and affections. Because you see, what I see here, you're proposing a kind of valence for affects and not so much for affections. So the distinction between affects and affection from a Deleuzian perspective is, I'm simplifying too much, but the essence of his thought here is that affects are the pure or raw and unprocessed data that all the inorganic and physical, organic or inorganic, and even physical systems can express. He even uses this term express unto the nature. But then again, when these affects, which are the stimuli, or let me say the constraints that have the capacity to affect a subjectivity, affect an observer, once they're processed by a subjectivity or an observer, they become affections, right? And the processed affections. So I was wondering, what do you think about this side of the processed affections? Because as far as I understood, your framework only describes the physical side, the unprocessed or let me say, filtered side of the physical expression of affects. So yeah, sorry for talking a lot, but yeah, those were my two comments I wanted to make. Thanks a lot.
Thank you. Yeah, I have to go away and think about the Deleuze. I mean, Spinoza is very important as well, because that's essentially where Fechner got this psychophysical framework from too. So it's going to be interesting to look at that. Just on time, very briefly, I didn't mention it, but in that table I showed you about halfway through, there's some time derivatives of these properties as well. So there's one called joy, I think, and one called shock, which are time dependent. And in fact, there's also an intensity property as well, which is a relationship between the amount of energy being transferred and the mass of the object, for example. So that may well fit in with what you say about, it's Eva Deli, isn't it? The paper. I haven't seen that preprint. I'd be interested to see it. If you can forward it to me, maybe.
Sure.
I've noticed some of their earlier work. Yeah, thank you. But no, I didn't talk about it. But time is a very important dimension, which and intensity, which is also linked to time, the duration of a valence event, for example, whether it happens very quickly with a lot of change in a small space of time or very slowly. That's probably going to make a big difference psychologically to the system as well. But it's very, very early days. I mean, these are all very speculative. It's only going to get really interesting when we start to test them in real systems and see if they play any role in the behavior. Yeah. Thank you.
Thank you very much for those questions. Do we have any more for now? Yes, please go ahead.
Yeah, Michael Trimble here. I'm terribly sorry, Karl, to bring this up again, but it has to do with music. But I just wondered, in a different angle, what you've been putting on, the images are superb. But I just wonder, are you one of the people that's been looking at Jackson Pollock's drip paintings or the pointillism of Seurat and Signac and whatever, who was said, I think, to have been influenced by a scientific background? And so what you were putting on was really lovely, and they're beautiful. And a lot of people think that some of those modern paintings are beautiful. I just like your comments on that. But just before that, following on from what we just heard, is quite fascinating, the difference between affect and affections. And you have to think of the art form which most is capitalized by energy sources and energy frequencies, and it's music. And I hope you have thought about this, but the whole business of music has to do with tension relief following tension increase. And, and the music is composed of components, of the loudness, the rhythm, the harmonies, whether the chords are discordant, whether you have perfect fifths or the devil's tone, the tritone, makes you feel better or worse. And this comes around what I just heard about the difference between affect and affections, if that was right. You have the basic affects within the music, but you have the affections, which are the responses to the music. And of course, you can't actually see music. And so music is more driven by principles which don't apply to most of the arts. And oddly enough, many people who talk about the arts forget about music. And I just one little comment. What you seem to have done is to be revising Sherrington's integrated action of the nervous system, which no neurologist can avoid. And I'm sorry, it's so fascinating, and thank you so much.
Thank you. Yes. Well, no, Sherrington is also a very important. There's one of my favorite books actually is his lectures that were published in 1940, that I forget the name of the title now, On Human Nature or something like that.
Yeah.
And he says, actually, he's very explicit in that book. He says everything is energy, you know, and that's all we know about in the world, the movement of energy, but we can't explain how that relates to the mind. And I think he actually said this is an embarrassment for biology. I think he uses that phrase. And so yeah, he's a very important figure. Music, you're absolutely right. In fact, for me, music's the easiest way to visualize this, kind of physically, in terms of the relationship between waves, the way waves interact, the entrainment of different parts of the brain as they respond to external audio intensities and frequencies and so on. And everything you said about tension, increase, reduction, returning to the, you know, the key, the key of the music, whatever that is, C major, it has to go back to that. So it deviates and comes back. Not necessarily, I know, but very frequently. And the pleasure and displeasure associated with those experiences. So I think there's a very interesting research to be done on mapping the auditory stimulus from music with the physiological responses to it, and looking for these energy differences when it's associated with pleasure or displeasure. Discordancy would be a really interesting example, you know, where irritating sounds, or, you know, really unpleasant sounds must be having some physiological expression in our brain, I guess, in our nervous system.
Yeah.
And looking for what the marker of that, or the signature of that would be, I think, really interesting, using this kind of psychophysical framework.
Yeah, I mean, a lot of that is being done now in terms of entrainment of music of all kinds, and looking at EEG patterns and things like this. Yeah. But it's quite fascinating that one half tone, the alteration of a semitone in a triad, leads from the major to the minor. And there are differences in the fMRI images of people listening to music, which is either major or minor. But these are embedded evolutionary principles as to how our brains work and are interlinked with the environment.
Absolutely.
Things in the jungle, things made you either run away or, in fact, listen. You know, and, you know, music is beautiful or it's not beautiful. And it's, you know, I'm just fascinated by what you've said, and thank you very much.
Thank you. Thank you for your comments. There's a lot of really interesting connections in there. Thank you. Yeah.
Great. Thank you very much for these questions. Do we have any more questions for now? Please let me know. Otherwise, I think it is time for you to take over, Karl. Karl, can you hear me?
No, I'm here. I was just looking for the last paper that spoke to that last point, and I'm not sure I found it, but never mind. I've got a representative one. That's good. Okay, so back to where we are. I'm trying to obscure the sun. My apologies. That was a wonderful presentation and equally wonderful discussion. So I think the best parts of the afternoon are now over. But I'll try and focus. I'm not going to address everything that's been spoken about, but just focus on substantiating some of the, I think, sort of key points that pertain to self-organizing beautiful systems that would endorse the argument that we've heard from a technical perspective. So I'm going to deliberately just be a physicist here and say, yeah, this is all spot on. And furthermore, there are some relatively simple mathematical principles that endorse this story. And I'm doing that because usually when people come to these meetings, they want to write a book or want to write a paper, but you've already done that. So there's not much that we can teach you. So I'm mindful of the next step in terms of underwriting the arguments for a more technical audience, should you want to do that. I'm not sure that that you would want to do that sole or on sole by yourself, but possibly with your physicist friend. That you could write a sort of something that a physicist would understand or an information theorist would understand, that articulates what you've been saying, but says, and look, this is the underlying first principle account that means that this must be true, in one sense, and specific sense of density dynamics of self-organization. So as usual, I picked out a number of papers, some of which you've already mentioned, speaking to the fact we're not going to tell you anything you don't already know. But for the people watching this recording and the people in the audience, just a couple of them you've already referred to, so I'll just reprise those, and some that you might not have come across, which are more mathematical and technical in nature. So to frame those papers, it struck me that there were sort of two, well, first of all, just standing back in terms of finding this one unifying explanation that has these different perspectives or takes that have this nice legacy, dating right back to the 19th century. It did strike me, you refer to active inference free energy principle, and in writing down the free energy principle, that really was the physics backstory that allowed you then to talk about active inference. So from my perspective, active inference is an application of the free energy principle, because the word principle in the free energy principle is used very much as a physicist would use it. It's a method. It's not a grand theory. It's not a grand. It's not a story. It's just a tool or a method, much like Hamilton's principle of least action that you would apply as a tool or a method to compute the trajectory of a rocket to the moon, for example, or throwing a ball, should you want to compute that trajectory. On that view, it strikes me that your narrative would be basically a psychophysical application of the free energy principle that immediately tells you that they have the same commitments. So active inference, the psychophysics you're bringing to the table, have exactly the same foundations. That can be read in a number of different ways. You're emphasizing the psychophysics aspect of it. One could have called active inference sentient behavior, and that would be another name that sort of spoke to this dual aspect of not just self making sense of a world, but organizing oneself actively within that world in a particular way. And the other common theme, I think, between these applications of the free energy principle is that they should be just a 21st century version of what we knew was true in the 19th century. And just to congratulate you on the scholarliness of it, of your presentation. I mean, you were talking about things that as an intellectual thug, as one of my mentors used to tell me, I have never heard of before, but you clearly have. So that was beautiful, and I presume that's all in the book. And if it's not, then you should keep on sort of going through the history, which I presume you could actually take right back to Plato, and if you really wanted to, just to show that these are just internally consistent recapitulations of the same basic insights. Certainly the free energy principle that we are associated with could equally be read as a mathematical 21st version of ideomotor theory from William James or the originators in Germany, or it could be read as a version of Helmholtz's notion of unconscious inference, or it could be read as analysis by synthesis by Neisser, or it could be read as perception of a hypothesis testing by Barlow. There is a really consistent and deep history here. And some people emphasize one aspect, and other people like yourself who are more, I think, so probably better read, emphasize others that you know, some people may have missed. I mean, the people that I normally, or we normally emphasize are Helmholtz, basically, and then putting action into the mix. Although, in fact, Helmholtz did actually write very, very clearly about active inference in his more physiological writings. That's what we would emphasize. But I also have friends like Mark Sohm who say, well, look, hang on. When Freud was you know, trying to get his mechanics together, he didn't study under Helmholtz, but certainly he would have known about sort of unconscious inference and Helmholtz's notion of neuronal energy, neuronal free energy. And Freudian free energy was just his take on this. So, you know, again, deep truths, but just articulated with a different kind of narrative, different kind of calculus, and a different sort of explanandum, you know, depending upon the interest of these people. Another sort of, you know, legacy would be the world of cybernetics, for example. You know, that would be another way of sort of appealing to the same kinds of notions. And I mentioned cybernetics because I think there are some really interesting links between where you started with the marbling of paper that can be linked to Turing pattern formation via Turing through Ross Ashby, through the Ratio Club, and their common interests in the principles of self-organization that leads to this individuation of selfhood in the sense of as each cell in the marbling is retained, but in a collective, which, you know, as you say nowadays, could be described in terms of a Markov blanket of Markov blankets, which of course is another way of describing Turing patterns. And of course, Turing was, at the end of his life, was very interested in the principles that underlie, the beautiful principles that underlie the formation of these patterns. So I think there's lots of really interesting links that you could now speak to say, you know, not only was it Faraday's beautiful principles, but this is what Turing died worrying about, having spoken to Ross Ashby, the father of the good regulator theorem, and the homeostat, speaking to all these links between, say, homeostasis, self-organization, steady states, time-independent or time-invariant solutions. So I throw that in because some of the examples that you brought to the table in terms of the marbling and the formation and self-assembly and maintenance of individuated patterns that possess Markov blankets, in the sense that there are boundaries, there are self boundaries, there are ego boundaries at the level of the, you know, the ink blobs, which need explanation. And I'm sure that you know, that's what Faraday, or based upon what you said, I'm sure that that's what Faraday had in mind in terms of the beautiful principles. That's one big theme. The other big theme is this physical divide between the seen and the unseen, or the illuminated and the dark, or the physical and the psychological. And I notice you use the word extrinsic in relation to one half of that dialectic, or that divide. And I thought that was very interesting, because that's the same semantics that one application of the free energy principle leads you to when writing down mathematically in terms of information theory what that psychophysical dual aspect means. So that's the other big point I'm going to speak to, just to give you a bit more ammunition, if you can engage a physicist to write down the equations for you, or you can copy them from literature, should you want to. So if you'll indulge me, I'm going to share my screen, and hopefully, I was just searching for something which. This is it. Yeah, I haven't had a chance to order this, so forgive me that the flow of the narrative will not be quite as useful as it could have been. But I was just searching for an example of this motivation for an application of the free energy principle to psychophysics in the spirit that you've described. And just as a sort of note of humility, the free energy principle is also dual to James's constrained minimum path entropy principle that he wrote down in 1980, which is exactly the same as the principle of maximum entropy production. So when it's not Karl Friston's free energy principle. I mean, it is, but it's also dual to the best of what 20th century physics had to offer in terms of the way that we observe and interact and engage with the physical world. So the forerunners of that were the maximum entropy principle. But when you apply the maximum entropy principle to paths and dynamics in the way that you were talking about, and specifically that would be entailed by music, then you move to something called the maximum caliber principle, which is also known. And I'm saying these things out loud. You don't have to take notes because this is being recorded, so you can go to Wikipedia and it'll all make sense because it's expressed much more concisely on Wikipedia. So what we're talking about is the maximum caliber principle, which is also known as the principle of maximum entropy production over time, which is also known as the principle of minimum path entropy, which is really just a statement of the principle of least action, which just is the free energy principle. So the free energy principle, it can either be read as a principle of least action, so coming back to it being just a method, like Hamilton's principle of least action, but specifically applied to paths, and more specifically in the context of measurement that implies an observer or a measurer. The path in question and the energy in question, noting that action is energy times time, pertains to the beliefs of the observer or the estimates or the measurements of the observer about the observed, which for us would be, the rest of the world or everybody else in our world. But the maths, I repeat, is universal across all of these formulations, whether you're talking about a path-integral formulation, the free energy principle, or James's principle of minimum path entropy. It's just the same thing. So if we wanted to apply that, and then you were I went off on one there, my apologies. So you were talking about the importance of putting forth this principle so that people could apply it empirically and make some testable predictions and possibly measure the increases or decreases in free energy that are being associated with pleasure and pain, respectively, of a very simple sort. I was trying to find an example where that has been simulated explicitly, but perhaps before. Well, no. This is not the one I wanted. There is another paper which actually plots the measurements or the simulated neuronal responses to transient increases in free energy that basically emulate an evoked brain response in exactly the spirit that you were intimating, using brain imaging, and then plotting the same results in terms of the displeasure or the surprise or the movement away from your most likely states, showing an almost linear relationship in terms of what you can measure neurophysiologically. So this is the result of a simulation, just showing you these transient episodes of surprise, so increasing in free energy if you square these things, that is reflected in an increase in the thermodynamic free energy of neural activity. So at its simplest, this paradigm has been used to great effect for many, many decades now under the rubric of something called the oddball paradigm. You may have come across it in terms of the mismatch negativity paradigm, and this is the experimental paradigm in which you introduce some comforting regularity and predictability, very much like the fruit fly enjoying itself on the turntable, or an autistic child's self-stimulating, and violating these this nice predictability, low free energy states from a psychophysical perspective, by introducing something that is discordant, if we were talking about musical perception or music perception, or just unpredicted, something out of place, and that would be the oddball. So you establish in these mismatch negativity paradigms, you use a very, very simple paradigm. You just go boop, 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 beep. And it's the beep, which is the oddball. And the beep induces surprise. And that surprise is an increase effectively in the psychophysical free energy. And that produces what's called a more exuberant electrophysiological excursion, that if you subtract the beep from the oddball boop, you subtract the standard from the oddball, then the difference is the extra evoked response, that is the thermodynamic, if you like, or the intrinsic brain expression of a local increase in thermodynamic free energy. So most of brain activation studies rely exactly upon this, that you're inducing surprise or displeasure, read simply as an increase in free energy, experimentally, and looking at which part of the brain was surprised or displeasured, as it tries to now explain this unpredictable, discordant sensory event, and retain and get back, having explained it, back to its homeostatic set points and free energy minimizing, resolving uncertainty. Oh, that was an oddball, or that was a deliberate violation of my musical expectations in some sort of modern jazz context. So I think that story could be very usefully unpacked just by noting effectively that's what people have been doing in cognitive neuroscience, and in particular in brain imaging electrophysiology, for decades, even if they didn't know they were doing it. And you can now sort of, say this is the pleasure principle, or the pain and pleasure principle, or psychophysics coming through, preempting the establishment of these kinds of paradigms, which now people use regularly to try and work out the functional anatomy, the computational anatomy of people's brains, and work out what are they surprised to? Is it violations of phonology? Is it violations of semantics? Are you surprised? This level of abstraction, trying to work out which parts of the system of the brain are actually responsible for that. So this was just a simulation of this, using an in silico brain, showing you these excursions from the thermodynamic or electrophysiological equilibria that can be simulated through belief updating in the context of presenting words that were not predictable effectively. So it's not music, this is language. It's not quite the one I wanted though, but it'll do just to make the point. Let me just come back to the this theme of pattern formation and self-organization, and I'm exemplifying this with what not a marble printing person would go to, but what a chemist or a physicist would go to, which is this famed BZ reaction, where these cells are self-organizing and self-constructing dynamically. This is the kind of sort of Turing pattern formation that Turing was trying to understand. What are the beautiful principles that explain this kind of self-organization? And the reason I frame it like that is that this kind of self-organization rests upon something which you won't find very much of in the 20th century physics. And I'm just wondering whether Faraday was actually speaking to 21st century physics, of non-equilibrium or far from equilibrium steady states. So you use the equilibrium word, which would have been fine in the day of Faraday and most of the 20th century. But in this century, the beautiful principle are the principles that underwrite non-equilibrium physics. So what you were talking about was exactly what you mentioned about 5 slides later, which is stability. It's that steady state. But that steady state is uniquely obtained when the system is open, when it's in exchange with other cells or other people or an environment. So the bright line between 20th century physics and equilibrium physics and 21st century physics and non-equilibrium steady states and physics is whether the system is closed or open. So if the system is closed, it'll just settle down to a steady state, and that would be the steady state that equilibrium physics applies to, the kind of physics you learned at school you'll find on Wikipedia. But that's not fit for purpose. There can be no beautiful principles there because you have to move to open systems. And now think about the mathematical differences between self-organization in open systems, which now requires you to define explicitly the difference between the self in self-organization and non-self, basically your heat bath or the environment or stuff out there. And that's where the Markov blanket comes in. So once you move to non-equilibrium systems, by definition, you're moving to the physics of open systems. Open to what? So immediately you have a fundamental task at hand, which is to disambiguate the thing that is being open and the thing that you're open to, and that boundary or that separation is just the Markov blanket. And then you can sort of recast this kind of pattern formation in terms of the dynamic construction and deconstruction, reconstruction of little Markov blankets, giving you your nice cellular pattern, your nice marbling, and the beautiful art. That there are patterns here. And one thing which characterizes this perspective on self-organization is its scale-free aspect, that there are cells of cells and cells of cells of cells of cells, in virtue of the fact that because you are now open, then you can now basically coarse grain microscopic patterns of the entire system to which you are open, and then find effectively cells or Markov blankets at the scale above, and so on ad infinitum. And I'm pretty sure that the beautiful principle would have to speak not just to the emergence of self-organization, where the self is defined by a boundary or a Markov boundary or a Markov blanket, but also the scale-free aspect, the fractional dimensional self-similarity implicit in a scale-free context. So I thought those were sort of mathematical, if like, endorsements of looking back and asking, are the beautiful principles of Faraday evident in modern day physics and self-organization? And I think the answer would be yes, absolutely. And these are exactly the questions that Turing was wrestling with. But people are still wrestling with them now. But they do point to, I think, a distinction between equilibria, which we do not want. So in this world, equilibrium means you're dead, or you've been sequestered and closed off from your lived world. What you're looking for is that stability or homeostasis or steady state in the setting of being open to a world or a universe which is referred to as a non-equilibrium or far from equilibrium steady state. And that's really where the homeostasis lies. It's getting back to your attracting set, and you just measure how close you are to your attracting set in terms of your pleasure and displeasure, which would just be the self-information. So there's a nice play on self here. Every time we sort of talk about these things, there's always either self-information, self-assembly, self-organization, So you then sort of just ask yourself the question, well, how do I define self? And of course, that's where the Markov blanket comes into the boundary between self and non-self. Self-similar. So whenever you talk about what the beautiful principles must either entail or evince, there's always a sort of self part to the pronoun or self to the phrase, certainly in the physics of this. So I thought that was a really interesting point. Well, it's interesting that you moved to homeostasis and stability and stop talking about equilibrium, because I think you'd have to and start talking about non-equilibrium steady states and non-equilibrium stability. And I think that would be, sorry to distract myself. Did you go to this? This was at York. Art and Affect in the Predictive Mind. It's about 3 or 4 years ago. It might be pre-COVID, actually. Well, no, I'm not sure.
Yeah, no, I wasn't there actually, but I know of it, and I know the people. Yeah, quite a few of those people. So yes, I think I've seen quite a few of the talks as well, including yours from that meeting. Yeah.
Brilliant. Yeah, and in fact, you then went on to author a piece in the special issue that was the key people from this meeting then were also invited to contribute, and particularly Sander. So I knew that, I guessed you'd know about this, so I'm just putting this up for everybody else who's interested.
Thank
it
you.
Might be.
Yeah.
It was a nice meeting of minds who had never met before, just to pursue this point of convergence between art and affect and predictive processing, that then gave rise to, as we've seen already, this issue of philosophical transactions. And this is not your paper, but it's in the same issue, just written by one of the key players, which was Sander van der Cruz, who has a particular perspective on this from, not your perspective, but a perspective, which I think I can't quite remember, but well, he may have also written the introduction to this, linking aesthetics and the predictive mind. So again, you know this, but just in case there are people watching who don't, that might be an interesting review of how one person or one group links aesthetics to predictive processing and surprise minimization or free energy minimization or pleasure. I think this, if you could engage a local physics friend, I think this paper would be useful from your point of view. So this is, let me remember where I am. Oh, that was silly. Page 40. So this has never been published. So it's on an archive, and it's really written for physicists, just taking you through all the aspects of all the physics you need to know to understand the beautiful principle as read as self-organization in the spirit of non-equilibrium steady states. But in getting to those first principles, you really have to grapple with the self-similarity of self-organization to minimize self-information. And it just takes you through, and this is from the perspective of the renormalization group, how Markov blankets and Markov blankets emerge. And it strikes me that's got to be part of your story, and it was implicit in one of your marble designs that there was a large ring around all the little rings, and in a sense it couldn't have been any other way if it is truly the kind of thing that exists in our lived world, simply because of the self-similarity aspect of things that self-organize. And it just takes you through the maths of that. So I thought that was, and I was just trying to hint at the self-similar aspect, just with these little cartoons of Mandelbrot sets there, but the same principles apply exactly in the construction of these things. And then there are people who have, in a more narrative way, sort of spoken about this, the Markov blankets of life with this sort of scale-free or scale-invariant aspect, that the same rules. If you read this as the beautiful principles apply at every scale of analysis, and always contextualize the scale above and the scale below. And I think this came from a group of philosophers in. In fact, me as well. But I was going to highlight Michael Kirchhoff, who's currently in Australia, who's written quite a lot about Markov blankets. But this person also was a friend of Sander, who was the senior author on that Proceedings B paper. So that was one interesting take. But what I wanted to do there was just imagining you going back to your physicist and saying, okay, how can we now create a simulation where we're simulating an idealized gas of little self atoms, all open to each other and open to a heat bath, and start to now simulate and measure their psychological states. And what I would recommend is that you basically treat each of the little atoms as its own Markov blanket. So in order to do that, you're going to have to get on the inside to get at the psychological states and to enumerate and to simulate them, and to show that the displeasure of a subtle increase in free energy or surprise, as represented by the beliefs on the psychological on the inside, do correspond to events induced by the outside, and also co-occur with the physical thermodynamic fluctuations in those internal states. Now, you can't do that in real life because you can't break someone's Markov blanket, because if you did, they wouldn't exist anymore. But you can do it in silico. So if you can simulate lots of little Markov blankets, so replace each of your atoms with a very simple little agent that has its own Markov blanket, so there's an inside. You've now got the opportunity now to simulate the beliefs of this atom as it gets surprised by bumping into its neighbor, which it didn't predict. And the simplest way to do that is to make each of your little atoms have autonomous dynamics and their own Markov blanket. And indeed, that was the basis of the primordial soup that you illustrated at the end with the Life as You Know It paper. So that was very similar to your simulations, but there was a twist here, that we were interpreting the inner atoms as on the inside a Markov blanket, so that one could deliberately now talk about the fluctuations in the actual physical chemical states at the same time as what those stood in for in terms of our psychological beliefs about what was beyond the Markov blanket. And this was actually rehearsed, where each little atom actually had autonomous dynamics in virtue of being equipped with the dynamics of the Lorentz system. This was actually rehearsed in this very long, dense paper for physicists to actually try and understand the mechanics of the relationship between these beliefs, the psychological side, as opposed to the physical side. I'm just trying to find a pretty diagram. Yeah. So this was a reworking of that, where we were just looking for the physical the fluctuations in the physical states that could be read as having representing psychological beliefs, in this instance interpreted as sort of Bayesian beliefs about the outside. So we were looking at these internal atoms with autonomous dynamics that were separated from the outside by a Markov blanket not seen here. So the blue are internal and the cyan are external. And these fluctuations here are basically the real motion of outside states that can sometimes be occasionally surprising and deviate. And the blue line and grey area correspond to the Bayesian beliefs of the internal states about the external states. And these are the internal states themselves. So this would be the biophysical states of the internal states, that when you overlay periods of surprise, like say an oddball stimulus in an oddball paradigm, or a discordant note or key in music, if you overlay them together, they look very much like real recordings from electrophysiology. So this is actually recordings of a monkey brain responding to these oddball events, these unlikely, surprising events, so your short-term transient displeasures, if you like. And these are the simulated responses, but these are the physical and these are the psychological. So this is just for one atom. But if you could now reproduce this for a gas of atoms, I think that would be quite remarkable. Then you can start to ask questions about how your atoms have beliefs when they collide into another atom. But to do that, you're going to, I think, have at least two scales in play. So each atom has its own set of states, and then there are lots of atoms, so that you can pursue that. So this is on archives, called a free energy principle for a particular physics. The play on words here is that here it's the physics of particles, where a particle corresponds to a self. I'm hoping that your physics friend will understand this. The maths is not terribly deep, but it is written for physicists. One thing I thought was just useful to say out loud. You were basically saying, look, there's some fundamental valence to our interactions with the world that basically means pleasure is a resolution of free energy, and indeed, just for everybody. So the paper that was being described earlier by Joffoli and Concurrently is here, emotional valence of the free energy principle, and in particular, we were talking about carving up different affective valenced states in terms of whether free energy is increasing or decreasing. So these are the changes in free energy, and this is the free energy itself. And what these co-authors did, they went beyond just pleasure and displeasure. They went on to sort of carve whole emotional spaces up, but that was the basic idea, which we've heard about. And it did strike me the way that you phrased this, and certainly you attributed this. I can't remember who you attributed it to, but I thought was quite a fundamental insight that displeasure is walking away from those states that are more likely, given the kind of thing that you are. And if you recognize that, then that is displeasure, and that is surprise or an increase in free energy, a violation of your homeostasis that is simply scored by a departure or a surprise, where you suddenly find yourself in a sensory state that is highly unlikely for you. So, if I'm listening to music and I'm suddenly hearing something that's very discordant, that's not characteristic of me enjoying some nice and appropriate music. Likewise, if I suddenly find my blood glucose to be extremely high, then that's not characteristic of me. It violates my homeostasis. So that's actually measured very, very simply in terms of the negative log of the probability of being in that state, and in particular the sensory state. So if something is very surprising, then it means that the probability is very small, given the kind of thing that I am, as is the log. Therefore, the negative log is very high. So the free energy or the surprise is very, very high. And the reason I'm working through that is that this quantity is absolutely central to all of physics, and certainly the free energy principle. It is, in information theory, known as self-information. So it is exactly the same quantity we were talking about before in terms of self-organization, trying to minimize on average self-information via some kind of self-assembly in order to maintain some kind of selfhood. at all self-similar scales. In physics, this is known as a Lagrangian. And the free energy is the thing that bounds this Lagrangian here, and everything. So this, what is this paper? This is, yeah, it's a pathological formulation of the free energy principle, which is speaks to this principle of least action perspective on the minimum path entropy formulation of the free energy principle. But I just wanted to basically point out that this is where it all starts. It just all starts with a basic description of some self or something that is equipped with a probability distribution over the characteristic states that you find this self or thing in. And if you violate that, then you can measure that in terms of the Lagrangian, which also determines all the flows and the forces. And indeed, from that one equation, you can then derive all of the free energy principle in this example, including the emergence of Markov blankets and strange loops right at the end. So that was the point I wanted to make there, that there's some sort of deep truth to displeasure being the increase in the free energy, the Lagrangian, the surprise, the self-information. It can't be any other way, because properly formulated, this just measures how far you are away from the states that would characterize you. And of course, if you never go back to those states, you wouldn't exist. So the whole point of existence is to keep yourself in those states that characterize you as the kind of thing you are. So by definition, you have to get back to and get the decrease in the free energy or the pleasure of getting back to your homeostatic non-equilibrium steady state or attracting set, which it has to be itinerant. So that, I thought that was an interesting point from my perspective. But I'll close now with, I think, probably something which is most important from your perspective on the psychophysical principle. This paper, if you haven't read it, I think you'll find really quite interesting. So this was written really for Alan Hobson to talk about consciousness with a lot of help from Vanya Weiss. So sentience and the origins of conscience, from Cartesian dualism to Markovian monism, and its basic message, all wrapped up in the normal rhetoric, is that there has to be, if there is a self so defined in terms of having a boundary in the form of a Markov blanket, there has to be two information geometries. And in this paper, those two information geometries were divided into an intrinsic geometry, which is the geometry that underwrites the thermodynamics. So it's actually the information geometry that defines Lagrangians or potentials expressed in terms of joules and Boltzmann's constants and the like, that you would use understanding neuronal dynamics if you're measuring brain activation, for example. At the same time, supervening on exactly the same dynamics is an extrinsic information geometry. And that's why I was intrigued you using the extrinsic word in reference to the psychological or possibly aspect that pertains to the information geometry of the beliefs encoded by beliefs about the outside encoded by the internal states. So this is where the Bayesian mechanics come. So this is thermodynamics or statistical mechanics, and this is the Bayesian mechanics, but they both supervene on exactly the same underlying system, which are the internal states. And that, I think, really neatly allows you to say that there are two information geometries here, and well, very brief. An information geometry is simply the geometry of a space where every point in that space corresponds to a probability distribution. So that basically means that you can understand this. If you change a probability distribution, then you're moving in this space, and it's a well-defined space that has equipped with a metric called the Fisher information metric, and it can describe the actual probability distribution of my neuronal firing, or it could describe the probability distribution encoded by my neural firing. And that basically means that if I move on this in this geometry, I update my beliefs, or if I have a brain activation, I move in this space as in a way that can be described in terms of the thermodynamic cost and the temperature changes, or under the thermodynamic energy cost under a given temperature. So it strikes me that this is exactly what you want to provide the mathematical image of the psychophysiological psychophysics. And it has this, I would say, it's two aspects of the same thing, and it can't be any other way on this construction. So I thought this was a nice endorsement of this psychophysics, illuminate the seen and unseen, or what is hidden and what can be seen of an observer herself. I thought it was a nice mathematical vindication of that fundamental dialectic. And the interesting, from your point of view, not only do they both supervene on the same thing, but they both share the same free energy minimum, which means that when you've resolved your surprise and you've found a good explanation for this piece of art, and you've engaged in all your pleasure and aesthetics, and you've found for this moment in time the free energy minimum, then at the same point you've also minimized your thermodynamic energy, and that's provably so by a whole bunch of theorems that can be articulated in terms of fluctuation dissipation or master integral fluctuation theorems, of which the Jarzynski equality is probably one of the most important. You don't need to remember this. All you need to know is that if you've minimized your free energy in the sense of surprise, in a psychological sense, then you have also done it in the most thermodynamically efficient way, because you've also got the same thermodynamic minimum. And that's described quite a long time ago by Biswa Singupta in terms of, and I think hopefully he actually appeals to the Jarzynski equality in terms of, yes, well, let's not go through that. So I was hoping that he would have the equations describing the work. Yeah, here we go. Yeah, equation 6. So I think that again is a mathematical vindication of your notion that if this perspective is right, then there should be some measurable thermodynamic correlates of this kind of psychophysical, this dual aspect self-organization that basically engages the Bayesian mechanics of the sort that the free energy principle talks about, but also from the point of view of James, that is implicit in measuring or observing something. And I repeat, it's information and efficiency in the nervous system in computational biology. And that's it. Good, stop sharing. That was
fantastic. What a delightful meeting.
Yeah. Thank you.
Sorry, I didn't want to steal your words, Robert.
Go ahead.
No, just a quick another unmute and round of applause for the brilliant presentation, Robert. Thank you very much. And sorry, I didn't want to interfere, Robert. Did you have anything more to say? Otherwise, I would close the meeting for today.
No, other than to thank everybody and particularly Karl for that. My mind is swimming, spinning, but it was very exciting actually to hear the ideas reflected back in that way, and to feel that there are these, to understand the depth and breadth of these principles and how they've been explored in so many different contexts, and yet seem to have this commonality and point us more or less in the same direction. And it gives me a great deal of optimism that this is within our grasp in some way, this realizing what these beautiful principles might be. So thank you. That was extraordinarily generous of you to share all that. Thank you.
Well, fantastic. Thank you very much. Thank you very much, everyone, for joining and the interaction and engagement. Thanks again, Robert, for your brilliant presentation, and thank you, Karl, for the extensive discussion. Look very much forward to seeing you again at the next TNV meeting. The next one is on Monday. And otherwise, have a lovely afternoon, everyone. Thank you very much.
Thank you, everybody.
Bye.